In the earliest age of the universe, and space is still filled with thick neutral hydrogen, and most young galaxies should remain hidden behind that ancient fog. But one distant galaxy seems to do the impossible. It clears a path through the darkness far too soon, sending a signal that should never have escaped. Tonight, this journey follows the galaxy that appears to break the rules of the early cosmos. If this kind of deep space mystery is fascinating, please like the video, subscribe to the channel, and stay with the story. At this point in cosmic history, the universe is still very young. It is only about 330 million years past the Big Bang, an age so early that nearly everything familiar from the modern sky is absent in its mature form. There are no great spiral systems with long settled arms. There are no richly layered clusters shaped by billions of years of slow encounters. There is no wide transparency from one end of space to the other. The large setting is simpler, dimmer, denser, and less finished. Space is already expanding, but it still carries the strong mark of youth. Matter has not yet spent long ages arranging itself into the complex patterns seen much later. Light exists, but it does not yet travel with easy freedom through every region. The broad universe at this time is filled mostly with hydrogen, the lightest and most abundant element. Helium is present as well, but hydrogen dominates the great stretches between the earliest gatherings of matter. Much of that hydrogen is neutral, which means each atom keeps its electron and remains whole, rather than separated into charged parts. In modern space, large volumes between galaxies are highly ionized and transparent to many forms of energetic radiation. Here, the situation is different. Neutral hydrogen spreads through the intergalactic medium, the enormous realm between galaxies, and it changes the behavior of light. It makes the universe resistant to certain light, especially the energetic light that young hot stars produce in abundance. In that resistance, the early universe keeps a kind of fog. This fog is not mist made of droplets. It is not cloud in any weather-bound sense. It is a vast condition of matter spread across cosmic distances. Neutral hydrogen absorbs and scatters some of the light that tries to move through it. Because of this, the universe is not yet widely transparent. Radiation can begin to carve through it only where strong local sources arise. The early cosmos, therefore, appears not as a smooth turning on of light everywhere at once, but as a slow and uneven struggle between opacity and clearing. In one region, energetic radiation begins to alter surrounding gas. In another, the old neutral state still holds. The setting remains mixed. Before this age, the universe passes through an earlier interval often called the cosmic dark ages. During that time, there are no stars yet shining through space. Matter exists. Gravity continues its patient work, and the background glow from the much earlier hot phase keeps stretching to longer wavelengths as the universe expands. But there are no stellar furnaces to brighten the young cosmos. Then gravity slowly deepens tiny differences in density. Slightly fuller regions pull in more matter. Gas gathers. The first stars begin to form inside the earlier small galactic structures. Their arrival does not instantly transform everything. Instead, each new source of ultraviolet radiation creates a local change, and the larger universe responds only in patches. This early stage of transformation is known as reionization. The term describes a change in the state of cosmic hydrogen. When energetic radiation removes electrons from neutral atoms, the gas becomes ionized. In the broadest sense, reionization is the gradual conversion of much of the intergalactic hydrogen from a neutral state into a charged one. That change matters because ionized gas is far more transparent to the kinds of radiation that neutral hydrogen blocks. As more stars and galaxies appear, more regions lose their neutrality. The fog begins to thin, but not in one clean advancing wall across the whole universe. It breaks apart in scattered zones around sources of light. These zones grow and eventually overlap, so the universe in this section is not fully dark, and it is not fully clear. It is transitional. It lives in the interval between the first appearance of luminous structures and the later time when intergalactic space becomes mostly transparent. This gives the cosmos an uneven geography even on enormous scales. One region may still be dominated by neutral hydrogen and remain highly opaque to certain emissions. Another may contain a pocket where radiation from young stars has already changed the state of the gas. The early universe is therefore patchy in a very physical sense. Its openness varies from place to place. The age of about 330 million years places the universe near the beginning of this process. Astronomers generally understand reionization as an extended era rather than a single event. It unfolds over hundreds of millions of years. By the time the universe reaches roughly 1 billion years of age, much more of the intergalactic hydrogen has become ionized. But at only a few 100 million years, neutral gas is still expected to be common. The wider environment should still be difficult for certain light to cross. This expectation forms the calm outer setting for the subject at hand. Expansion also shapes everything in this young universe. Distances between unbound regions continue to increase, and the wavelengths of light stretch as they travel. Radiation emitted in the ultraviolet or visible range arrives much redder after crossing such immense distances. This stretching is what allows astronomers to place very distant galaxies in time. The farther back the source lies, the more strongly its light is shifted toward longer wavelengths. A galaxy seen from this age therefore appears not only remote in space but remote in history. Seen on the widest scale, the early universe is a young expanding medium governed by simple physical conditions. Gravity gathers matter into the first concentrated structures. Hot young stars begin to produce powerful radiation. Neutral hydrogen still occupies much of the space between those structures. Reionization has started, yet it has not advanced far enough to clear the cosmos in any complete way. The result is a universe that remains partially veiled. It is luminous in points, resistant in between, and uneven across vast reaches. Within this large and quiet setting, every ancient galaxy must exist inside the general rule of the time. It forms in a universe where transparency is local, not global. It shines into surroundings that are still mostly capable of stopping delicate signals before they travel far. The outer region is therefore not just background, it is the governing condition. At 330 million years after the Big Bang, the cosmos is already awakening, but it is not yet awake. The early universe does not change state in a smooth and even way. Its great fog of neutral hydrogen thins irregularly, with clearings appearing in some places while other places remain closed. This unevenness is one of the defining features of the reionization era. Space is not divided into simple layers, one fully dark and one fully clear. Instead, it becomes mottled. Across immense distances, the intergalactic medium develops a patchwork structure made of neutral regions that still hold on to their electrons and ionized regions where energetic radiation has already separated atoms into charged parts. This patchiness begins with the way matter is distributed. Even in the earliest universe, matter is not perfectly uniform. Tiny differences in density, present from very early times, grow slowly under gravity. Slightly denser places gather more gas and become the first sites where stars and primitive galaxies form. Less dense places remain quieter for longer, because radiation comes from these concentrated islands of activity. The transformation of hydrogen begins around them rather than everywhere at once. The cosmic fog therefore breaks where sources exist. It endures where sources are absent, weak, or too far away. A region of ionized hydrogen forms when ultraviolet radiation from hot stars removes electrons from nearby atoms. At first, this affects only the immediate surroundings of a source. The change zone is small compared with the great volume of neutral space around it. But if the source continues to shine, and if enough energetic light escapes from the dense gas close to the stars, the ionized region grows. It spreads outward into the intergalactic medium, consuming neutral hydrogen atom by atom. This growth is not always steady. Gas density varies. Fresh neutral gas can flow inward. Recombination can also occur, which means an electron rejoins a proton and the atom becomes neutral again. The balance between ionization and recombination helps determine whether a clear region expands, stalls, or contracts. Because all of this depends on local conditions, the large map of the early universe becomes highly uneven. Some regions host several young galaxies close together. Their radiation fields can overlap and strengthen one another. In such places, a larger ionized zone may develop earlier than average. Other regions contain fewer sources and remain mostly neutral. Distance matters as well. Even a bright source cannot immediately affect gas across enormous cosmic spans. Its radiation must travel outward, and the universe is still dense enough that energetic photons are readily consumed. Each clear region is therefore local before it is global. The edges between these regions are not like hard walls. They are transition zones shaped by density, temperature, radiation intensity, and time. In one area, hydrogen may be almost fully ionized. In a neighboring area, it may still be mostly neutral. The change can be gradual in some directions and sharper in others. This gives the early universe a textured quality. It is not a simple fog bank lifting evenly from a landscape. It is more like a wide field of openings with uncertain boundaries, scattered through a much larger dimness. This patchwork has direct consequences for what can be detected across deep time. A signal leaving one young galaxy may pass through a favorable region where hydrogen has already been altered, while a similar signal from another galaxy of similar brightness may encounter mostly neutral gas and be lost. For this reason, visibility in the early universe depends not only on the source itself, but also on the state of the surrounding intergalactic medium. The environment becomes part of the observation. The universe does not merely contain early galaxies, it filters them. Astronomers therefore think of reionization not only as a change in time, but also as a change in geography. At any single moment during this era, different parts of space can sit in different states. One area may already be relatively transparent to some kinds of ultraviolet light. Another may still absorb it strongly. This means there is no single universal condition that applies everywhere at once. The young cosmos is a mosaic. Its pieces evolve at different rates according to local structure and local sources of radiation. The patchiness also reflects the fact that the earliest galaxies are modest in size compared with many later systems. Their influence can be powerful nearby, but it is not limitless. Their light must push against a medium still rich in neutral hydrogen. Their star formation can be intense, yet the reach of its effect depends on how long it lasts, how many massive stars form, how much radiation escapes from dense gas, and how quickly surrounding atoms return to neutrality. The universe at this stage is dynamic, but it is not yet dominated by a single connected transparent web. At this stage, separate ionized pockets remain distinct more often than not. Neutral space still fills much of the volume between them. The fog is no longer complete, yet it remains the governing medium. Open regions resemble islands in a wider sea of unaltered hydrogen, and their distribution follows the hidden pattern of early structure. Dense places host more activity. Quiet places keep their neutrality for longer. The result is a universe whose openness varies from region to region across vast distances. In this outer environment, scale is essential. Each local change occurs within a much larger background that has not changed yet. A galaxy can reshape its immediate surroundings without transforming the whole age in which it lives. This is why the patchy nature of reionization matters so deeply. It allows exceptions in one place without requiring the entire universe to behave the same way. It allows an early source to sit inside a local opening while the larger cosmos remains largely closed. So the early universe in this region is neither uniformly opaque nor uniformly clear. It is a scattered terrain of neutral expanses and ionized pockets, governed by density, radiation, time, and the fragile balance between atoms losing electrons and reclaiming them. The fog persists, but it no longer persists in one unbroken piece. It is being pierced in many separate places, each one temporary or growing according to local conditions. In that broken pattern, the great outer setting takes on its true form. Between the observing instruments of the present age and the distant source lies a line of sight of immense length. It crosses not empty nothingness, but the intergalactic medium of a very young universe. This path is the next outer region of the subject. It is the route along which ancient light must travel, and it is also the region that decides whether that light survives in a form that can still be recognized. The source may emit energy with great strength, but the line of sight has its own authority. It filters, weakens, redirects, and sometimes removes the most fragile signals long before they can complete the journey. In the modern universe, many such long journeys take place through intergalactic space that is largely ionized and comparatively transparent. In the early universe, that is not yet the normal condition. Neutral hydrogen remains widespread, especially at the age considered here. This matters because neutral hydrogen interacts strongly with certain wavelengths of light, and one of the most sensitive of these is the Lyman alpha line. This line is produced by hydrogen itself under specific atomic conditions, and it becomes one of the most valuable traces in the study of very distant galaxies. Yet it is also one of the easiest signals to disturb. A long path through neutral gas is usually enough to erase it from clear view. The problem is not only absorption in the simple sense of light vanishing at a single point. Neutral hydrogen can also scatter this radiation. A photon that begins its journey in one direction may be redirected many times. Even if it is not destroyed, it can be removed from the clean beam that would otherwise carry it toward a telescope. Over vast distances, repeated scattering turns a sharp and identifiable signal into something diffuse, displaced, or lost. The line of sight therefore acts less like a window and more like a difficult medium through which only certain kinds of light pass cleanly. At this age of the universe, the great distance to the source means that the light spends much of its existence moving through a cosmos still close to the reionization era. Along the way, the state of hydrogen may vary from region to region. Some stretches may be relatively open, having already become ionized by nearby sources. Other stretches may remain stubbornly neutral. The total journey is therefore not defined by a single condition repeated evenly across space. It is a sequence of environments. Each part of the line of sight has its own density, temperature, ionization state, and velocity structure. All of these affect how the signal changes as it travels. This is why the detection of certain light from extreme distances is never only about the source itself. It also depends on what lies between source and observer. A galaxy can produce a strong hydrogen signal in its own neighborhood, and yet still remain invisible in that line after the signal crosses enough neutral gas. The line of sight becomes an active participant in the observation. It is part of the measurement, part of the obstacle, and part of the explanation. Cosmic expansion adds another layer to this journey. As light moves through expanding space, its wavelength stretches. Radiation emitted in the ultraviolet arrives much redder after crossing such enormous distances. This gradual shift can sometimes help a photon move away from the precise wavelength most strongly absorbed by neutral hydrogen. Even so, the early stages of the journey remain crucial. If the photon begins in or near a region where neutral hydrogen is abundant, it may be scattered before redshifting enough to escape the worst of that interaction. The path is therefore sensitive to the order of conditions encountered. What happens close to the source can shape the rest of the voyage. The line of sight also passes through structure on many scales. On the widest scale, it traverses the large pattern of the young universe, including under dense regions, denser filaments of matter, and local ionized pockets around active sources. On smaller scales, it encounters variations in gas density that change the number of hydrogen atoms available to interact with the radiation. A denser stretch presents a more difficult crossing. A thinner stretch may permit greater survival. The journey of a single signal is therefore tied to the invisible geography of the early cosmos. Because of this, astronomers often treat the transmission of light through the intergalactic medium as a probability rather than a certainty. A photon at a vulnerable wavelength is not guaranteed safe passage, even if the source is bright. Its fate depends on the amount of neutral hydrogen encountered, on the arrangement of ionized and neutral patches, and on the details of local motion in the gas. The long line of sight is a statistical landscape. Some routes remain blocked. Some routes permit partial escape. A few routes may remain unusually open. In this region, distance is not passive length. It is accumulated interaction. Every additional stretch of early intergalactic space gives neutral hydrogen another chance to interfere. The farther back in time the source lies, the more demanding the path becomes, because more of the journey occurs through a universe that has not yet finished clearing. For very early galaxies, this difficulty is expected to be severe. Signals that depend on delicate passage through hydrogen should often be muted or absent after such a long crossing. This expectation creates the calm physical background for the puzzle. A distant source from this era should send its light through a largely hostile medium. Its most sensitive hydrogen signal should face repeated opportunities for scattering or absorption. The line of sight should behave as a barrier far more often than as an open corridor. When a fragile signal survives such a route, the path itself becomes part of the mystery. Either the route is more open than usual, or the conditions near the source have altered the early stages of travel in a significant way, or both. So this third region is the great intervening space itself, the long and difficult road between a young galaxy and a present-day observatory. It is filled with hydrogen, structured by the uneven progress of reionization, stretched by expansion, and governed by the ordinary physics of atomic interaction over extraordinary distances. In this region, light does not merely move, it negotiates. It passes through a medium that tests every vulnerable wavelength, and in doing so it reveals how much the universe between galaxies still matters. Against that difficult background, one source stands out with unusual force. It is catalogued as JADES-GS-Z13-1, a remote galaxy seen at a time when the universe is only about 330 million years old. In ordinary terms, this places it among the earliest known galaxies whose light has been studied in detail. It does not appear in a mature cosmic setting. It does not belong to an age when intergalactic space has already become widely transparent. It is seen during a period when much of the wider universe should still be filled with neutral hydrogen. That alone makes any clear detection from such a source significant. But this galaxy is not merely present at an early time. It shows a kind of signal that makes it far more striking than a distant point of light. The galaxy enters the scientific record through the remarkable reach of the James Webb Space Telescope and the careful analysis of its infrared data. Because the universe expands, light from such a remote source arrives stretched to longer wavelengths. Radiation that begins in the ultraviolet is shifted into the infrared by the time it reaches modern instruments. Webb is designed to work in exactly this domain. It does not bring the early universe close in any physical sense, but it makes that ancient light measurable. In doing so, it reveals not only the existence of very early galaxies, but also the physical character of their light. JADES-GS-Z13-1 belongs to a group of objects found in deep surveys aimed at the earliest cosmic epochs. In these surveys, many remote sources appear faint, redshifted, and difficult to distinguish from one another without careful spectral confirmation. A distant galaxy must first be identified as a likely candidate, then studied more precisely to determine how far back in time it truly lies. This source survives that process and becomes one of the confirmed galaxies from a remarkably early era. Its distance is therefore not a loose impression. It is tied to measured features in its light that place it firmly in the very young universe. Even before one considers the most surprising part of the observation, the galaxy is already notable. It is present at a time when galaxies are expected to be small, rapidly forming, and still assembling their mass. It belongs to a universe in which stars have only recently begun transforming the wider medium. In that sense, it stands near the opening chapters of ordinary galaxy growth. Yet what makes it memorable is not simply that it exists so early. It is the way it announces itself through hydrogen light that should have found the journey difficult. That is why it can be understood as an unexpected beacon. The word beacon is useful here not because the galaxy is gigantic by later standards, but because its light carries unusually far-reaching implications. A beacon is a source whose visibility tells something about its surroundings. This galaxy does exactly that. Its signal is not only evidence of a distant object, it is evidence that something about the conditions around it, or along the early part of its path, differs from the simplest expectation for such an early time. The source, therefore, becomes more than a point in a catalogue. It becomes a physical clue. The galaxy is also understood as a youthful system. Its light indicates an active and energetic population of young stars rather than an old settled stellar body. In the early universe, this is not surprising in itself. Most galaxies at such an age are expected to be dominated by recent star formation. Their stars are young because there has not yet been time for a long-settled history to accumulate. Their structures are compact because the larger grand forms seen in later cosmic ages usually require more time to develop. The importance of JADES-GS-13-1 lies in how clearly such a young system is detected under conditions that should still suppress one of the most delicate signals in its spectrum. So the galaxy occupies a careful balance between the ordinary and the extraordinary. It is ordinary in the sense that it belongs to the era of first galaxy growth, where compact systems of young stars are expected. It is extraordinary in the sense that one of its defining observed features appears earlier than many astronomers would expect to see so clearly. This balance matters. The object does not overturn the basic existence of early galaxies. Rather, it sharpens attention on the local conditions that may allow one particular galaxy to appear with unusual clarity. Its importance also comes from timing. At 330 million years after the Big Bang, the Reionization era is still young. Neutral hydrogen should still dominate much of intergalactic space. For this reason, a galaxy from this period would normally be expected to show signs of that wider opacity. Some of its light may still reach a telescope, especially once redshift carries it into observable infrared wavelengths. But a fragile hydrogen signature should often be reduced or absent. JADES-GS-Z 13-1 does not fit comfortably within that quiet expectation. It appears too communicative for its age. This is why the galaxy attracts such focused attention. It is not just distant. Distance alone is no longer the whole surprise in the age of Webb. The telescope has already revealed a population of early galaxies, some brighter and more structured than earlier models had anticipated. What singles out this source is that it seems to speak through a medium that ought to muffle precisely the feature by which it is heard most clearly. Its light reaches across a universe that is still young, still mixed in its ionization state, and still resistant in many regions. Yet the source is seen not as a vague suggestion, but as a confirmed object with an unexpectedly revealing signal. In this way, JADES-GS-Z13-1 becomes a fixed point within the broader mystery of the early universe. It is not the entire story of reionization, and it is not a final answer to how the first transparent regions grow. It is one observed galaxy, but it is a galaxy that seems to stand in a place where silence is more expected than clarity. The source is early, compact, youthful, and distant, and still it manages to emerge with unusual strength from a time when the universe should still be difficult to read. So this section settles on the galaxy itself as the first clearly bounded object within the larger setting already described. The young universe surrounds it. Patchy hydrogen still fills much of space beyond it. A long and difficult line of sight separates it from the present. Yet here, at last, there is a single source with a name, a measured age, and a presence strong enough to alter the mood of the entire problem. JADES-GS-Z13-1 is not merely another early galaxy. It is the one that appears too early, too clearly, and too distinctly to be easy to ignore. Around the galaxy, the surrounding space is not expected to remain in exactly the same state as the wider young universe. Even in an age when neutral hydrogen still fills much of intergalactic space, a strong source of radiation can alter its immediate environment. This next region is that altered environment. The local ionized bubble around JADES-GS-Z13-1. It is not the whole universe becoming clear. It is a nearby volume of gas that has been changed by the galaxy's own energetic output. Within this region, hydrogen no longer remains mostly neutral. much of it has been stripped of its electrons, turning the gas into a more transparent state and allowing delicate light a better chance to move outward from the source. The existence of such a bubble follows from ordinary physics. A young galaxy filled with hot, massive stars releases ultraviolet radiation in large amounts. Some of that radiation is energetic enough to ionize hydrogen. If it escapes from the dense gas near the stars, it begins to work on the surrounding medium. Neutral atoms in the nearby intergalactic gas lose their electrons. The local state of matter changes. Instead of a fog of intact hydrogen atoms, the region becomes a volume of ionized gas in which protons and electrons remain separated for a time. In this state, the gas is much less hostile to certain emissions that would otherwise be scattered or absorbed close to the source. This change does not happen all at once. At first, only the nearest gas responds. The effect begins close to the galaxy, where the radiation field is strongest. As long as the galaxy continues to produce enough ionizing light, the transformed region can grow. Every newly ionized atom makes the immediate surroundings more open, which helps energetic photons travel farther and continue the process. The bubble therefore develops through persistence. It is not a brief flash. It is the cumulative result of radiation acting over time in a local cosmic neighborhood. The shape of this region is not likely to be a perfect sphere. Real gas is not arranged with smooth symmetry. Density changes from place to place. Streams of material may be falling inward. Hot gas and radiation may move more easily through thinner channels than through denser ones. The local bubble is therefore best understood as an irregular volume surrounding the galaxy rather than a clean geometric shell. In one direction it may extend farther. In another it may remain more compact. Yet despite these irregularities, the essential idea is simple. The galaxy lives inside a pocket of altered hydrogen, and that pocket is more transparent than the larger young universe beyond it. Time is central to this region, at only 330 million years after the Big Bang. The universe is still young, and any galaxy within it has had limited time to build up long-lasting effects. For a local ionized bubble to become significant, the source must either shine with unusual strength, shine efficiently for a sustained period, or occupy an environment where the surrounding gas is especially favorable to clearing. The bubble therefore records a local history. It reflects how much ionizing power the galaxy has delivered into its neighborhood and how effectively that power has changed the nearby medium. This nearby transparency matters because the earliest stage of a photon's journey is often the most vulnerable. If delicate light begins its passage inside dense neutral gas, it may be scattered before cosmic expansion can shift it away from the most dangerous wavelength. But if that light starts inside a local region already cleared of much neutral hydrogen, it gains a better initial path. The bubble acts as a zone of relief. It does not guarantee full escape across the wider universe, but it allows the signal to begin moving outward under more favorable conditions. For a galaxy such as JA-DES-GS-Z-13-1, this local clearing is not a minor detail. It may be the central reason its signal can survive at all. The bubble is also a measure of contrast. Inside it, hydrogen is in a changed state. Outside the most altered region, the young universe still remains far more neutral. The difference between these two conditions gives the galaxy a local domain distinct from the age around it. This is why a single source can appear clearer than the wider cosmic era would suggest. The large universe may still be resistant, but the small neighborhood around one energetic galaxy can already be open enough to let key signals travel their first crucial distance. recombination continues to matter within this region. Ionization does not end the story by itself. Free electrons and protons can join again, rebuilding neutral hydrogen. In denser gas, this can happen more quickly, which means the bubble must be maintained by a continuing supply of energetic radiation. A local clear region therefore exists through balance rather than permanence. The galaxy must keep replenishing the ionized state against the natural tendency of matter to return to neutrality. This gives the bubble a dynamic character. It is not a frozen cavity. It is a living local condition sustained by current physical processes. Its size is therefore not determined by brightness alone. It depends on the number of ionizing photons the galaxy produces, the fraction that escape into the surrounding gas, the density of that gas, and the amount of time over which the source remains active. A lower density environment can be cleared more readily. A higher density environment requires more sustained effort. The bubble is thus the product of source and setting together. It belongs to neither alone. The galaxy provides the power, while the surrounding medium sets the resistance. In this region, one begins to see how a local exception can exist inside a generally opaque age. Reionization on the grand scale is still incomplete. Much of the universe remains neutral. Yet around this galaxy, enough radiation may have accumulated to create a substantial pocket of ionized gas. That local openness does not contradict the youth of the universe. It expresses the patchy nature of the era. The bubble is an island of changed matter formed around one active source, a small transparent province within a much broader realm of incomplete clearing. So the local ionized bubble is the first truly intimate environment of the galaxy. It is not yet the stars themselves, or the dense body of the system. It is the immediate cosmic space around the source, shaped by its radiation and held in a delicate balance between continued ionization and returning neutrality. In this region, the galaxy begins to alter the universe around it rather than merely sit inside it. The change is local, irregular, and time-dependent, but it may be strong enough to matter decisively. Here, close to the source, the young universe is no longer simply given. It is being actively remade. Beyond the local ionized bubble, the state of hydrogen changes again. This boundary region is the edge where a relatively open neighborhood meets the more neutral medium of the early universe. It is not a sharp wall in any simple visual sense, yet it behaves as a decisive frontier for light. Within the bubble, hydrogen is largely ionized, and certain fragile signals can begin to move outward with less resistance. Beyond that bubble, neutral hydrogen becomes far more common again, and the journey changes character. The signal that matters most here is the Lyman alpha line, a particular form of hydrogen light that is especially vulnerable to neutral gas. At this edge, the difference between survival and erasure often depends on how much neutral hydrogen lies ahead and how far the photon has already travelled before meeting it. Neutral hydrogen interacts with Lyman alpha light with exceptional strength. A photon at just the right wavelength is readily absorbed and re-emitted, or scattered out of its original path. In a medium where neutral atoms are common, this interaction becomes relentless. A clean beam does not remain clean for long. The photon may still exist after an interaction, but it no longer continues along the same simple route toward a telescope. It changes direction, it can diffuse through space, and it can lose the sharp observational identity that makes it useful as a direct signal from a distant galaxy. This is why the outer neutral medium matters so much. It does not need to destroy every photon outright. It only needs to interrupt the ordered passage enough to erase the line from clear view. The edge of the ionized bubble is therefore a critical place. If the bubble is small, Lyman alpha photons leave the galaxy and soon encounter a heavy field of neutral hydrogen while still close to the wavelength most easily scattered. Their chances of clean escape become poor. If the bubble is larger, those same photons spend more time moving through ionized space before they reach mostly neutral gas. During that interval, cosmic expansion continues to stretch their wavelength. By the time they arrive at the neutral edge, they may have shifted enough to reduce the worst of the interaction. The bubble does not remove the problem entirely, but it changes the conditions under which the problem begins. That difference can be decisive. This means that the size of the bubble is not simply a geometric curiosity. It directly affects transmission. A larger bubble gives the photon distance and time. A smaller bubble exposes it too early. The edge becomes a threshold whose position determines whether a delicate signal enters hostile territory in a vulnerable state or in a slightly safer one. In the young universe, where much of the wider medium is still neutral, this threshold carries unusual importance. A source with a sufficiently extended ionized region may become visible in a way that another similar source cannot. Shape matters as much as size. Because the bubble is unlikely to be perfectly symmetrical, its boundary does not sit at the same distance in every direction. One path outward may pass through a longer stretch of ionized gas, while another may meet neutral hydrogen sooner. The escape of Lyman alpha light is therefore directional. In some directions the galaxy may have an easier opening, in others it may face rapid suppression. The neutral edge is not only a ring around the galaxy, it is an irregular frontier with different levels of permeability depending on direction. Density matters as well. Neutral hydrogen does not have identical thickness everywhere just beyond the bubble. Some regions contain more atoms per unit volume, and therefore present a stronger barrier. Other regions may be thinner, with a smaller chance of repeated scattering. Motion in the gas also plays a role. If the surrounding medium is moving relative to the source, the exact wavelength seen by local atoms can shift slightly, changing how strongly they interact with the passing photon. The neutral edge is therefore not just an abstract border between two states. It is a physical region with density structure, velocity structure, and varying optical depth, meaning varying resistance to light. The word optical depth is useful here. It refers to how difficult it is for radiation to pass through a medium. A region with high optical depth strongly blocks or scatters the light in question. A region with low optical depth allows more transmission. For Lyman alpha in a neutral early universe, the optical depth is often extremely high. This is why the line is such a sensitive tracer of reionization. Its visibility immediately says something about the hydrogen environment around a source. When the line appears strongly from a very early galaxy, attention naturally turns to the neutral edge around its bubble, because that is the region most responsible for deciding whether the signal can emerge in recognizable form. The edge is also dynamic. It can move outward if ionizing radiation continues to win against recombination and against the supply of fresh neutral gas. It can remain close if the source is weaker or the surrounding medium denser. It may advance faster in one direction and more slowly in another. This makes the frontier a record of local history. Its present position reflects past radiation output, past gas conditions, and the ongoing contest between clearing and neutrality. In this region, the galaxy's light no longer moves through territory fully shaped by the galaxy. It begins to encounter the larger authority of the early intergalactic medium, yet the local bubble still leaves its mark, because the bubble determines where that encounter starts. The neutral edge is therefore a meeting place between local and cosmic conditions. It joins the immediate influence of one young galaxy to the wider state of the universe at that age. A signal that survives this meeting carries information about both. So the intergalactic hydrogen edge is not merely the outside of the bubble. It is the controlling boundary that tests the escape of hydrogen light, its distance from the source, its shape, its density, and its degree of neutrality all matter. At this frontier, the young universe resumes its ordinary resistance. Neutral hydrogen becomes dominant again, and the fragile line faces the medium that usually suppresses it. Whether that line remains visible depends strongly on how this edge is arranged. In that sense, the mystery is written not only in the galaxy itself, but in the exact place where its cleared neighbourhood ends and the old cosmic fog begins, closer to the galaxy, but still outside its bright stellar body, lies a more immediate borderland of gas. This region is neither the broad intergalactic medium nor the dense interior where stars form. It is the circumgalactic medium, the gas that surrounds the visible galaxy and links it to the wider universe. In a very young system such as JADE S-GS-Z 13-1, this borderland is likely compact by later cosmic standards, yet it remains physically important. It is the zone where inflowing material, outflowing material, radiation, and gravity meet. It is also the zone through which energetic light must pass after leaving the galaxy itself, and before entering the more distant surroundings beyond. This gas is not static. It does not rest in a simple shell around the source. Some of it is moving inward, drawn by gravity as fresh material continues to feed the young galaxy. Some of it is moving outward, pushed by the effects of intense star formation. Hot stars emit radiation and drive energetic processes into nearby gas. Stellar winds and the deaths of short-lived massive stars can add further motion, heating some material and pushing it away from the central body. The circumgalactic region is therefore a place of exchange. Matter is not merely sitting there, it is circulating, cooling, heating, compressing, and dispersing. In a young galaxy, inflow matters because growth is still rapid. Gas from the surroundings continues to fall inward, adding fresh hydrogen and helium to the system. Without this supply, star formation would soon weaken. The circumgalactic medium acts as the first reservoir from which the galaxy continues to draw. Some inflowing streams may be relatively cool and dense compared with the hotter material around them. Such streams can carry matter inward efficiently, especially in the early universe where galaxies are still assembling quickly. This means that even while the galaxy clears and ionizes part of its environment, it also remains connected to surrounding neutral or partly ionized gas that gravity keeps pulling inward. Outflow matters for the opposite reason. Where young stars are numerous and luminous, their energy does not remain confined to the stellar body. Radiation pressure, stellar winds, and the heating of gas by energetic photons can push material outward into the circumgalactic zone. In some places, this creates lower density paths through which radiation can escape more easily. In other places, expelled gas can collect into denser structures that hinder transmission. The region is therefore neither simply open nor simply closed. Its effect on light depends on how gas is arranged and how it moves at a given time. This borderland is likely clumpy. Gas density changes from place to place rather than remaining smooth. Some pockets are denser and more resistant to radiation. Others are thinner and more easily ionized. This unevenness is important because ionizing photons do not need every direction to be equally open. If only a fraction of paths out of the galaxy are relatively clear, radiation can still leak into the surroundings and help sustain the local ionized bubble. The circumgalactic medium therefore acts less like a solid barrier and more like a porous screen. Its degree of porosity determines how much of the galaxy's energetic output can escape. That porosity depends on structure. Dense clumps absorb radiation efficiently and can preserve neutral hydrogen within them. Lower density gaps allow photons to move farther before being stopped. A galaxy surrounded by many thick neutral clumps may produce large amounts of energetic light and still fail to affect its environment strongly if most of that light remains trapped. A galaxy with more fragmented or channeled gas can have a much larger influence even if its intrinsic power is similar. The arrangement of matter in this borderland is therefore a central part of the problem. It mediates between the radiation made by stars and the wider region that radiation tries to transform. The circumgalactic medium also affects the special hydrogen signal already described. Lyman alpha photons do not simply emerge from the visible galaxy into empty openness. They first move through this surrounding gas, where scattering can already reshape the line before it ever reaches the larger intergalactic medium. If the nearby gas is rich in neutral hydrogen, the line can be broadened, redirected, or suppressed at very short range. If local outflows shift the gas motion in favorable ways, the photons may leave the immediate surroundings with less severe interaction. The borderland thus imprints its own effect on the signal before the more distant universe begins to act on it. Motion is especially important here. Gas moving away from the galaxy changes the relative conditions seen by escaping photons. In some circumstances, this can help photons emerge from the immediate region with wavelengths that are slightly less vulnerable to resonant scattering by nearby neutral hydrogen. Gas moving inward can have the opposite effect, keeping the photons closer to the most strongly interacting condition. The details are subtle, but the general result is clear: kinematics, meaning the pattern of motion in the gas influences escape. Temperature matters too. Hotter gas tends to be more diffuse and more ionized, while cooler gas can remain denser and more neutral. In a young galaxy, these phases may exist side by side. Hot material created by energetic stars or shocks can fill part of the circumgalactic volume. Cooler clumps or streams can pass through or remain embedded within it. The borderland is therefore multiphase, meaning it contains gas in more than one physical state at the same time. This layered structure makes the escape of radiation highly dependent on path and direction. Because the galaxy is so young, the circumgalactic medium likely reflects a system that is still actively building itself rather than one that has reached long-term equilibrium. There has not yet been time for a settled outer atmosphere to form in the later and more orderly sense seen around many mature galaxies. Instead, the region remains busy with assembly. Fresh matter arrives. Radiation pushes outward. Gas heats and cools. Some material becomes ionized, while some dense pockets remain more sheltered. The borderland keeps changing as the galaxy grows. In this region, the visible source and the wider universe are joined by a zone of negotiation. The galaxy does not deliver its light directly into open space. It must first pass through gas that both belongs to the galaxy's environment and connects it to the surrounding cosmos. This gas can block, scatter, shift, or channel the escaping radiation. It can feed future stars while also carrying away the effects of present ones. It can hold on to neutral hydrogen in dense pockets while allowing more transparent routes elsewhere. So the circumgalactic borderlands form a narrow but decisive region around JADES-GS-Z13-1. They are active, structured, and unsettled. They receive matter from outside and energy from within. They decide how much of the galaxy's radiation truly escapes into the larger surroundings. They are not the source of light itself, and they are not the broad early universe beyond, but they stand between the two and shape the connection. In this borderland, the young galaxy's influence is filtered through moving gas, uneven density, and partial openness, and the outcome of that filtering may determine how clearly the galaxy can alter the space around it, enclosing the circumgalactic gas and shaping the entire local system is a larger and more elusive structure, the dark matter halo. Dark matter is the name given to matter that does not shine or absorb light in the ordinary ways used to see stars and gas, yet reveals its presence through gravity. A halo is the broad, roughly rounded region in which that unseen matter gathers around a galaxy. In the case of a very young galaxy, such as JADES-GS-Z 13-1, this halo is one of the most important hidden parts of the system. It is not directly observed as a glowing object, but it provides the gravitational frame within which the visible galaxy forms, holds together, and continues to grow. This region is larger than the bright body of the galaxy and more enduring than any single burst of star formation. Its gravity draws in ordinary matter, meaning the hydrogen and helium gas that can cool, condense, and eventually take part in making stars. Without such a gravitational structure, gas in the expanding early universe would have much greater difficulty remaining concentrated for long. The halo therefore acts as a gathering ground. It gives the young galaxy a place where matter can collect rather than simply disperse with cosmic expansion. In the early universe, this role is especially important because galaxies are only beginning to assemble. The first structures do not emerge from a blank and random spread of matter. They arise because dark matter begins clustering earlier and more effectively than ordinary gas. It does not collide, radiate, or cool in the same way as gas, so it can start building dense gravitational scaffolding while the universe is still very young. Ordinary matter then falls into these growing concentrations. The halo comes first as a structure of gravity, and the visible galaxy grows inside it as gas responds to that hidden pull. This makes the halo a kind of deep container, though not a container with solid boundaries. Its edges are gradual, and its matter is spread diffusely over a large volume. Yet its gravitational influence is real and decisive. It determines how strongly the system can hold on to gas. A more massive halo exerts a deeper gravitational pull, making it easier to retain inflowing material and harder for energetic processes to drive all the gas away. A lighter halo provides a weaker hold and is more vulnerable to losing matter when stars begin releasing energy into their surroundings. The halo therefore sets the basic scale of what the young galaxy can keep, gather, and continue to use. In this region, gravity is the essential language. The visible brightness of a galaxy may rise and fall as stars form and die, but the halo remains the broader structure that organizes the motion of matter over longer spans of time. Gas falling inward does so because the halo has created a gravitational well, which is a region where matter tends to move inward under the pull of accumulated mass. The deeper the well, the more strongly matter is drawn toward the center. In a young system, this affects how quickly gas can assemble, how dense the inner regions may become, and how much raw material remains available for continued activity. The halo also influences temperature indirectly. As gas falls into the gravitational potential of the system, it can heat up. Whether that gas then cools efficiently enough to move farther inward depends on the balance between heating and cooling processes in a young galaxy where matter is still arriving rapidly. This balance can be delicate. If gas remains too hot for too long, It does not condense easily. If it cools effectively, it can flow inward and help sustain vigorous growth. The halo therefore governs not only where gas goes, but also the conditions under which it settles. Because JADES-GS-Z 13-1 is observed at such an early cosmic age, the nature of its halo becomes part of the broader puzzle. For the galaxy to appear active and influential so early, it must exist within a gravitational setting capable of gathering enough ordinary matter quickly. Observations indicate a compact and youthful source with strong radiation, and such a source usually requires an underlying reservoir of gas that has been assembled with unusual efficiency for that era. The halo is the most likely structure to provide that reservoir. This does not mean every detail of its mass is known exactly. It means the galaxy's visible behavior points to an unseen gravitational framework that is already doing substantial work. The halo is also where the balance between inflow and feedback begins to take on larger meaning. Feedback is the effect that stars and other energetic processes have on their surroundings, especially when they heat gas or push it outward. In a shallow halo, feedback can have a more disruptive influence, because the system struggles to hold on to matter once it is disturbed. In a deeper halo, the same energetic effects may stir the gas without removing too much of it. Material can be pushed outward for a time and still remain gravitationally bound, later cooling and moving inward again. The halo therefore shapes not just accumulation, but resilience. It determines whether the system can continue building after energetic events, or whether it is easily exhausted. Another important feature of the halo is that it does not exist in isolation from the large-scale structure of the young universe. It forms where matter has gathered more strongly than average, often connected to wider filaments of cosmic material that continue to supply fresh gas. The halo is therefore both a local structure and a node within a larger network of gravitational flow. It concentrates matter into a galaxy-sized system, while still remaining linked to the broader distribution of mass in the early cosmos. In this way, the halo turns the large environment into local growth, even though dark matter cannot be seen directly. Astronomers do not treat the halo as an optional idea or decorative theory. It is a practical necessity in modern understanding of galaxy formation. The visible matter alone does not explain how structures of this kind gather and persist so effectively, especially at very early times. The halo is the hidden architecture of the system. It provides the mass that ordinary gas responds to, and through that response it sets the stage for everything the visible galaxy can become. Uncertainty remains in the details, as it often does for extremely distant objects. The exact mass of the halo, the full pattern of matter within it, and the precise speed of its assembly are not all measured directly. Observations indicate the presence of a substantial gravitational framework, while it remains uncertain exactly how unusual that framework is compared with other young galaxies from the same era. But this uncertainty does not weaken the importance of the region itself. It only means that the hidden structure is inferred through its effects rather than seen in direct light. So this region is the invisible body around the visible source, the broad dark matter halo that gathers matter, deepens gravity, and gives the young galaxy a durable framework. It holds the circumgalactic gas within a larger field of attraction. It governs how much material can remain bound, how readily fresh gas can be drawn inward, and how strongly the system resists disruption. In this quiet, unseen region, the galaxy's future possibilities are shaped long before they appear as light. The halo does not shine, yet it determines how much shining matter can exist within it, and in a universe still near its beginning, that hidden control is profound. Inside the dark matter halo and within the surrounding borderlands of gas sits the visible body of the galaxy itself. This is the compact young galaxy, the luminous central system that instruments actually detect as a concentrated source of ancient light. At the distance and age involved, the galaxy does not appear as a grand rotating form with wide settled arms or a broad disk extended across space. It appears small, bright, and intensely concentrated, a young assembly of stars and gas occupying a limited region within a much larger gravitational framework. This compactness is one of its defining qualities. It tells of a system still close to its beginning, where matter has gathered quickly and where luminous activity is crowded into a relatively narrow volume. A compact galaxy in the early universe is not unusual in the broadest sense. Young systems often begin as dense concentrations before later mergers, extended growth, and long internal rearrangements produce larger and more elaborate forms. But in a case such as JADES-GS-Z 13-1, compactness carries special weight because it combines with great distance and strong emission. A great deal of energetic activity seems to be present inside a small physical body. This means the galaxy is not only present very early, it is also active enough within its limited size to leave a detectable mark on its surroundings. The visible body is made of ordinary matter, mostly hydrogen and helium gas, along with the young stars that have already formed from part of that gas. Some heavier elements may already be present in small amounts, produced by earlier generations of massive stars that live briefly and return enriched material to their environment. Even so, this is not a chemically mature galaxy by later standards. It belongs to a time when the universe has had only a short interval for repeated cycles of star birth and stellar death. The visible body therefore reflects youth not only in structure, but also in composition. It is a system still close to the original cosmic supply. Its brightness suggests a concentrated period of recent star formation. Light from young galaxies in the early universe is often dominated by hot newly formed stars, especially the most massive among them, because these stars shine intensely even though they live for only short spans. If many such stars form within a compact region, the galaxy can appear surprisingly luminous for its size. This does not require it to be enormous in total mass. It requires that a meaningful fraction of its available gas is turning into stars rapidly enough to produce a strong collective output. The visible body thus becomes the immediate stage on which rapid early assembly is written in light. Compactness also affects the internal density of matter. When gas and stars are concentrated within a smaller space, interactions become more immediate. Radiation fields are strong. Stellar feedback, meaning the effects of young stars on nearby gas, can become intense. Because the sources and the surrounding material are close together, a compact young galaxy may therefore evolve quickly. Its gas can be heated, compressed, dispersed, and ionized on relatively short timescales. The visible body is not a quiet arrangement of stars settled over long ages. It is an active concentration where gravity and radiation work in close quarters. At this scale, the galaxy's appearance to observation is shaped by both its true structure and the limitations of extreme distance. The light reaching the telescope is faint in absolute terms after such a long journey, and the source is seen from a time when the universe is still very young. Even so, the data indicate a small, youthful object rather than a diffuse or fully developed system. This compact impression aligns with modern understanding of many early galaxies. Their light often comes from concentrated star-forming regions rather than the broad, mature bodies familiar in nearby cosmic space. In this region, Small size does not imply weakness. It can instead signal focused intensity. The visible galaxy is also where the ordinary material of the system begins to differentiate into internal roles. Some gas remains in reservoirs that have not yet formed stars. Some is actively collapsing into dense regions. Some has already become stellar matter. Some is being altered by the radiation of young stars. These transformations happen inside the central body, rather than in the broader outer regions already described. The compact galaxy is therefore the first place where matter is clearly arranged into a living internal system rather than a surrounding medium. It has an interior logic of its own. Even if that logic is still young and unsettled, its youth is visible in the balance of light. In older galaxies, long-lived cooler stars can dominate much of the visible mass and give the system a more stable and settled character. Here, by contrast, the light appears strongly weighted toward recent formation. This suggests that the galaxy is being seen during an active stage rather than during a quiet pause. It is in the midst of building itself. Its central body is not merely storing stars that formed long ago, it is radiating from events that are still fresh in cosmic terms. Rapid assembly is one of the most important ideas contained in this region. For a galaxy to be compact, young, and yet sufficiently luminous at such an early age, matter must have gathered efficiently. Gas must have moved inward, cooled, and condensed on timescales short enough to produce a dense, bright system, while the universe is still only a few 100 million years old. This does not mean every step is fully measured in detail. Observations indicate a concentrated and youthful source, while it remains uncertain exactly how unusual its assembly history is compared with other galaxies of the same epoch. Still, the visible body itself points clearly toward effective early growth. This central concentration also helps explain why the galaxy can influence its immediate environment. A dispersed system of the same total light might couple to its surroundings differently. In a compact body, many energetic stars occupy a smaller region, and the local radiation field near the center becomes stronger. That does not guarantee easy escape of ionizing light, since dense gas can also trap radiation, but it does mean the central source has the intensity needed to matter. The visible body acts as a concentrated engine rather than a loose scattering of faint parts. At this level, the galaxy becomes more than an entry in a survey. It becomes a physical object with shape, density, youth, and luminous concentration. It is small in extent, yet rich in activity. It is early in cosmic time, yet already organized enough to produce a coherent observable presence. Within the halo, within the surrounding gas, and within the broader reionizing universe, this compact body serves as the immediate seat of light. Its stars and gas occupy a narrow region, but what happens there reaches beyond that narrowness into the conditions already described. So this section settles fully on the visible galaxy as a compact young system, concentrated in size, bright in output, and still actively assembling its ordinary matter into a luminous body. It is not grand in the later sense. It is not settled. It is not diffuse. It is dense, youthful, and energetically alive. In that compactness lies much of its significance. A small early system, intensely active within a confined space, becomes capable of standing out across a universe that is still learning how to become transparent. Within the compact visible body of the galaxy lies the next inner region, the star birth reservoirs. These are the stores of gas dense enough, cool enough, and concentrated enough to become the immediate material for making new stars. They are not yet the stars themselves. They are the matter from which stars are drawn. In a very young galaxy such as JADES, GS-Z13-1. These reservoirs are central to everything the system becomes. They determine how much light can be produced, how quickly the galaxy can grow, and how strongly it can influence the space around it. At this depth, the galaxy is no longer considered mainly as a bright object in the sky. It becomes a working body of gas under pressure, gravity, and radiation. Most of this reservoir is hydrogen, with helium present as the next major component. Small amounts of heavier elements may already exist, but the gas remains comparatively simple in composition when judged against later cosmic ages. Even so, simple does not mean inactive. The gas is already undergoing constant change. Some parts remain relatively diffuse and do not yet take part directly in star formation. Other parts have become denser through the pull of gravity, through compression by local motions, or through the effects of energetic processes within the galaxy. The starbirth reservoir is therefore not one uniform cloud. It is a collection of gas structures at different stages of concentration. For stars to form, gas must lose enough internal support for gravity to pull it inward. Internal support comes from motion, temperature, magnetic effects, and local turbulence, meaning irregular chaotic movement within the gas. When support weakens or gravity gains the upper hand, a region begins to collapse. In the early universe, this process can happen quickly in places where matter is already strongly concentrated. JADES-GS-Z13-1 appears to be a galaxy where such concentration is well underway. Its brightness implies that parts of its gas reservoir are not only present, but actively turning inward towards stellar birth. Cooling is a key part of this process. Gas that stays too hot resists collapse because hotter material exerts greater pressure outward. To continue condensing, the gas must release energy and cool enough for gravity to compress it further. In the early universe, cooling pathways are not always as rich as they are in later galaxies, because the supply of heavier elements is still limited. Heavier elements and dust can help gas cool more efficiently. In a very young system, the gas may have fewer of these aids, which means the conditions for star formation can differ from those in more mature galaxies. Even so, observations indicate that early galaxies can still form stars at substantial rates, showing that their gas reservoirs do find ways to condense and collapse. Density is therefore one of the defining features of this region. The brighter the recent star formation, the more likely it is that a significant fraction of the gas has reached high density in compact zones. These dense regions are the direct nurseries of stars. They may be small in size compared with the visible body of the galaxy, but they hold great importance because this is where gravity overcomes resistance. In a compact galaxy, these nurseries may lie relatively close together, allowing many sites of stellar birth to exist within a confined volume. The result is concentrated activity rather than widely spread quiet formation. The reservoirs are also temporary in a profound sense. Gas does not remain forever in the same condition. Some of it collapses into stars, some is heated by nearby radiation and pushed back into a more diffuse state. Some may be expelled from the immediate region by feedback. Some may flow inward from neighbouring parts of the galaxy and replenish what has been used. The starbirth reservoir is therefore not a static storehouse. It is a transit state in the life of matter. Gas enters it, lingers in unstable balance, and then leaves by becoming stars or by being redistributed. This instability is especially important in a young active galaxy. The very stars that form inside the reservoir begin altering it almost immediately. Massive young stars emit intense ultraviolet radiation. They heat nearby gas, ionize it, and create expanding regions of altered matter around themselves. Their winds stir the surrounding medium. Later, some of these stars end their short lives violently and return energy and newly made heavier elements to nearby gas. Because of this, the reservoir is always being shaped by both birth and disruption. It creates stars, and those stars immediately begin changing the conditions under which more stars can form. In a compact early galaxy, this back and forth may be especially strong. Dense gas lies close to energetic stars, which means feedback does not operate at great distance. It acts nearby and often quickly. In one part of the reservoir, compression may trigger fresh collapse. In another, heating may halt it. Some gas may be broken into denser fragments, while some may be dispersed. These star-birth reservoirs therefore contain no simple pattern of steady usage. They are a field of competition between collapse and disturbance. Their total mass matters greatly. A galaxy can only sustain luminous star formation for as long as enough suitable gas remains available. If the reservoir is large and efficiently replenished, the galaxy can continue shining strongly. If it is small or quickly disrupted, the bright phase fades. In the case of JADES-GS-Z 13-1, the observed luminosity suggests that a meaningful amount of dense gas is present or has very recently been present. The galaxy does not appear as a relic of star formation long since completed. It appears as a system still drawing current power from the fresh conversion of gas into stars. These reservoirs also help explain how a young galaxy can influence reionization locally. Ionizing radiation comes from stars, but stars come from dense gas. The strength of the radiation field therefore begins here, in the ability of the galaxy to gather and maintain star-forming material. Without such reservoirs, the larger bubble of ionized gas around the galaxy would not be sustained. The early universe would remain unchanged nearby because the source itself would be too weak. The star-birth reservoirs are thus the buried origin of the galaxy's broader effect on its environment. Uncertainty remains in the detailed internal structure, as it must for such a distant source. No direct image can map every dense cloud within the galaxy. Observations indicate strong recent star formation and a compact active system, while it remains uncertain exactly how the gas is divided among dense clumps, diffuse regions, and short-lived collapsing cores. Yet the existence of substantial star-forming reservoirs is strongly implied by what the galaxy emits. The light seen at great distance requires a local supply of gas ready to become stars or already in the act of doing so. So this inner region is the working substance of the compact galaxy, the dense reservoirs of gas from which its light is continually renewed. They are simple in composition but complex in behavior. They cool, condense, fragment, and collapse. They are heated, stirred, ionized, and partly dispersed by the stars they produce. They do not sit quietly within the galaxy. They move through an unstable cycle that determines how much of the galaxy's mass becomes luminous and how much energy is released into the surrounding space. In these reservoirs, the galaxy's visible power begins not as finished light, but as vulnerable gas gradually surrendering to gravity, deeper inside the star-birth reservoirs. The next region is the population of massive hot stars themselves. These stars are the most powerful ordinary engines in the young galaxy. They do not live long, they do not form quietly, and they do not shine with gentle steadiness across vast ages. Instead, they burn rapidly, intensely, and with great influence on everything around them. In a system such as JADES-GS-Z 13-1, their importance is difficult to overstate. They provide much of the radiation that makes the galaxy bright. They shape the gas from which future stars may form. They fill the local environment with ultraviolet light, and that light is energetic enough to ionize hydrogen, meaning it can strip electrons from atoms and leave the gas in a charged state. A massive star begins in the same way as any other star, through the collapse of dense gas under gravity. But because more matter gathers into its forming core, the inward pressure becomes greater and the central temperature rises more sharply. Once nuclear fusion begins, hydrogen in the core is turned into helium, and the energy released from that process pours outward. In a very massive star, this energy output is immense compared with that of smaller stars. The star becomes hotter at its surface, more luminous across the spectrum, and especially strong in ultraviolet radiation. It is this combination of heat, brightness, and short life that gives such stars their role in the early universe. They're not likely to be the most numerous stars in the galaxy, because smaller stars generally form in greater numbers, but they dominate the energy budget. A large population of faint low-mass stars can contain much of the long-term stellar mass. Yet a smaller number of massive hot stars can produce a disproportionate share of the galaxy's immediate light and nearly all of its most energetic radiation. This is why the youthful brightness of a distant early galaxy so often points toward recent massive star formation. When such stars are present in sufficient numbers, the whole galaxy can appear more luminous and more influential than its total size alone would suggest. Their lives are brief because they burn through fuel at a rapid pace. A smaller star can conserve its hydrogen and shine for billions of years. A massive star consumes fuel much more quickly and therefore spends itself in only a few million years. In cosmic terms, this is almost immediate. The galaxy is caught during one of these bright, brief intervals, while many hot young stars are still alive and radiating strongly. That timing matters. The observed galaxy does not merely contain stars, it contains a stellar population whose most energetic members are still in their prime. The heat of these stars shapes nearby gas even before their radiation is considered in detail. A hot star does not rest neutrally inside a cloud. It warms and alters the material around it. Gas close to the star becomes ionized and expands outward as its temperature rises. This creates local cavities and fronts of change inside the galaxy. Dense material may survive in some clumps, but more diffuse gas is readily transformed. In a compact galaxy with many young hot stars, such effects overlap and accumulate. The stellar population becomes not just a source of light, but an internal force that continuously rearranges the medium from which it emerged. Ultraviolet radiation is the most important part of this influence. Because these stars are so hot, they emit strongly at wavelengths capable of ionizing hydrogen. This makes them prime candidates for driving local clearing in the early universe. A galaxy filled with such stars can create a large supply of ionizing photons, which are the individual packets of light that carry enough energy to separate electrons from atoms. Whether those photons all escape the galaxy is another matter, determined by gas structure and porosity, but their production begins here. The massive hot stars are the origin of that energetic output. Their brightness also affects how the galaxy appears in the ultraviolet continuum. The smooth range of light underlying individual spectral features. A very blue ultraviolet continuum often indicates a youthful stellar population dominated by hot stars. Since hotter stars emit a larger fraction of their light at shorter wavelengths. In an early galaxy, this blue light helps astronomers infer recent vigorous star formation. It is one of the broad signs that the stellar body is not old and settled, but newly active The visible brightness of JADES-GS-Z 13-1 is therefore not just a general glow. It points toward a specific kind of stellar population, one rich in hot, short-lived sources. These stars also begin changing the chemical state of the galaxy. Although they spend only short lives on the main sequence, meaning the long, stable phase of hydrogen fusion, they move quickly toward later stages and eventual death. During their lives, and especially at their endings, they contribute heavier elements to the surrounding gas. In a very young galaxy, this enrichment is still at an early stage, but it has already begun. The first generations of massive stars do not merely shine. They start to remake the composition of the system. Even a small amount of enrichment can affect future cooling and future star formation. Because the stars are massive, they are often found in groups rather than in complete isolation. Star formation frequently occurs in clustered fashion, where many stars arise from related dense structures in the gas. If several massive hot stars form close together, their combined radiation becomes especially powerful. Ionized regions overlap, feedback strengthens, and the local environment is reshaped more quickly. In a compact early galaxy, this clustered behavior can make the central stellar population act like a collective engine rather than a set of separate sources. The group becomes more important than any single star. The balance between creation and disruption is therefore intense in this region. Massive stars are born from dense gas, yet once formed they begin dispersing, heating, and ionizing that same environment. They support the galaxy's brightness while also limiting the conditions that created them. This does not make star formation impossible. It makes it self-modifying. New stars arise, and those stars immediately alter the next generation's birthplaces. In a young compact system, that cycle can proceed rapidly, giving the galaxy a highly dynamic inner life. Observations indicate that ordinary stellar radiation is likely to explain much of the galaxy's energetic output. While it remains uncertain whether stars alone account for every feature of the signal, this uncertainty does not weaken the importance of the stellar population. It only marks the difficulty of separating all possible sources at such distance. The stars themselves remain the most direct and physically expected engines of ionizing light in a young galaxy. They are the first explanation because they are the natural consequence of the dense gas and youthful brightness already established. So this inner region is the beating stellar core of the young galaxy, not in the sense of a single center, but as a concentrated population of massive hot stars whose light dominates the system's present state. They form quickly, burn fiercely, and live briefly. They flood nearby gas with heat and ultraviolet radiation. They create ionized zones, drive local change, and provide the immediate luminous power that allows the galaxy to stand out across a still resistant universe. In these stars, the galaxy's youth becomes visible as energy. Their brief bright lives are the simplest and strongest reason the system can clear, shine, and matter so early. From the massive hot stars, the next inner process is the escape of ionizing light. This is the stage at which radiation leaves its stellar birthplace and tries to move outward through the gas of the galaxy. Ionizing light means light energetic enough to remove electrons from atoms, especially hydrogen atoms. It is the form of radiation most responsible for changing neutral gas into ionized gas. In JADES-GS-Z 13-1, this process matters because the stars may produce a large supply of such light, but production alone is not enough. The decisive factor is how much of that light avoids being trapped inside the galaxy and reaches the surrounding medium. At this level, the mystery becomes a matter of passage. A young galaxy can contain many hot stars and still fail to affect its surroundings strongly if most of their ionizing radiation is absorbed close to where it is made. Dense gas is highly effective at intercepting energetic photons. Dust, if present, can absorb part of the radiation as well. The inner regions of star formation are therefore not automatically transparent to the very light they generate. In fact, they are often the first obstacle. The same dense gas that allows stars to form can also confine their influence. This creates a tension at the heart of the galaxy. Light is produced in abundance, yet much of it may be consumed locally unless there are paths through which it can leak outward. Leakage does not require the whole galaxy to become empty or clear. It requires unevenness. If the gas around young stars is clumpy rather than smooth, some directions may contain lower density channels. Through those channels, ionizing photons can travel farther before being absorbed. This is why porosity becomes so important. A porous medium is one that contains openings or thin regions through which radiation can escape. In a compact active galaxy, feedback from young stars can increase that porosity by heating gas, expanding ionized cavities, and pushing material aside. What begins as a dense star-forming environment may gradually open into a more channeled structure. These channels are not stable tunnels cut once and left unchanged. They are temporary features created by ongoing physical processes. A burst of star formation may ionize and push aside nearby gas, making escape easier in one direction. Later, fresh inflow or shifting material may partially close that route. Another region may become more open as stellar winds clear its surroundings. The leakage of ionizing light is therefore variable in space and time. A galaxy may be leaky along some lines of sight and much less leaky along others. It may also become more or less transparent over relatively short cosmic intervals. This directional dependence is important. The galaxy does not need to release ionizing light equally in every direction to create a significant local effect. If enough photons escape through a limited number of openings, they can still ionize surrounding gas and enlarge the local bubble. From far away, the result may be a galaxy that seems unusually effective at clearing its environment, even though much of its radiation remains trapped inside other parts of its own body. Leakage is therefore not an all-or-nothing condition. Partial escape can still be astrophysically powerful. The structure of the gas close to the stars governs this process. Dense clumps behave like shields. More diffuse regions behave like windows. If feedback fragments the gas into knots separated by thinner gaps, the effective escape fraction can rise. Escape fraction is the share of produced ionizing photons that actually leave the galaxy rather than being absorbed internally. This quantity is central to reionization studies because it links stellar production to intergalactic change. A galaxy may create many ionizing photons, but only the escaping fraction contributes directly to clearing hydrogen beyond the galaxy itself. In very young galaxies, escape fractions may differ from those in later mature systems because the internal structure can be more chaotic and compact. Rapid star formation, strong feedback, and unsettled gas flows may create conditions in which some pathways open more readily. At the same time, high gas density can also keep many photons trapped. The outcome depends on details of geometry, density, and motion. Observations indicate that early galaxies are capable of contributing to reionization, while it remains uncertain how high the typical escape fraction is for any single source. For an object such as JADES-GS-Z 13-1, An unusually favorable internal structure may be one reason its surrounding region appears more cleared than expected. The escape of ionizing light also depends on timing within the life of stellar populations. Very young, massive stars emit strongly in ionizing wavelengths, but the gas around them may still be dense if star formation has only just begun. As feedback proceeds, nearby gas can become more disrupted, opening routes of escape. This means there can be a delay between the birth of hot stars and the moment when their radiation escapes most effectively. The most influential phase may occur when stars are still young and luminous, yet their surroundings have already been partly cleared by earlier feedback. A galaxy caught during that interval can appear especially effective at ionizing its environment. Once ionizing photons reach the circumgalactic medium, their influence expands beyond the immediate stellar body. They begin converting nearby hydrogen into an ionized state, helping sustain and enlarge the local bubble already described. This outer effect depends entirely on successful inner escape. Without leakage, the circumgalactic and intergalactic gas remain much less altered. With leakage, a compact galaxy can influence a surrounding volume far larger than its visible size. The small stellar core then gains a reach that extends into the cosmic medium around it. There is also an observational consequence. A galaxy that leaks ionizing radiation efficiently may be more likely to show signs of local clearing that help other fragile signals survive. This does not mean ionizing photons and every observed spectral feature behave in identical ways, but it does mean the underlying openness of the environment can be related. If ionizing light escapes well, the surrounding hydrogen becomes less neutral, and the path for sensitive emissions can improve. Leakage therefore links the inner engine of hot stars to the larger scale evidence seen by telescopes. At this depth, the galaxy is best understood as a source whose true power depends not only on what it makes, but on what it releases. The stars generate the radiation. The gas determines how much of that radiation remains bottled up and how much reaches open space. The shape of the galaxy's internal matter becomes as important as the brightness of its stars. A dense compact system can still become influential if its gas is sufficiently broken, channeled, or disturbed. A luminous system can remain locally ineffective if its gas stays too closed. Passage is the key. So this region is the process by which ionizing light leaks out of the young galaxy through imperfect openings in its own gas. It is not a smooth flood moving equally in all directions. It is a selective outward passage shaped by clumps, gaps, motion, and timing. Here the compact galaxy either keeps its power close or begins to project it into the wider universe. In JADES-GS-Z 13-1, the evidence suggests that at least some of this light escapes well enough to matter. The galaxy's surroundings do not clear by accident. They clear because the radiation produced in its interstellar population finds ways to leave home. Still deeper within the compact galaxy lies a more uncertain possibility: the presence of a central black hole that is actively gathering matter and releasing energy. This kind of source is often called an active galactic nucleus. The term refers not to the black hole alone, but to the luminous activity produced when gas falls inward, heats strongly, and radiates before crossing the point of no return. In many galaxies across cosmic history, such central activity can become one of the brightest features in the entire system. In JADES-GS-Z 13-1, this possibility is treated with caution. Observations indicate a remarkable early galaxy with unusual emission properties, while it remains uncertain whether part of that signal comes from an active central black hole rather than from stars alone. A black hole is a region where gravity has become so strong that within a certain boundary, called the event horizon, escape is no longer possible. A supermassive black hole, the kind usually associated with galactic centers, does not shine by itself. It becomes visible only when matter approaches it. Gas falling inward forms a rotating structure around the black hole, often called an accretion disk. Friction, compression, and extreme heating within that disk cause the gas to radiate intensely. This radiation can cover a wide range of wavelengths and can sometimes rival or exceed the light from all the stars in the surrounding galaxy. If such a source exists in JADES-GS-Z13-1, it would matter because active black holes can produce large amounts of energetic radiation in a compact region. They can ionize nearby gas, alter the circumgalactic environment, and contribute to clearing surrounding hydrogen. In that sense, a central black hole could help explain why the galaxy appears unusually capable of carving out a transparent zone so early in cosmic history. A compact and powerful central engine would add to the ionizing budget already supplied by massive hot stars. It would provide another way for a small young system to have an outsized effect on its surroundings. The challenge is that very distant galaxies are difficult to interpret with complete confidence. Their light travels for immense stretches of time, arrives faint and red-shifted, and must be analysed through limited spectral features. A galaxy dominated by hot young stars can produce some observational signatures that overlap with those expected from an active nucleus. Both can create hard radiation fields. Both can ionize gas. Both can shape emission lines in ways that complicate interpretation. For this reason, astronomers do not treat the active black hole explanation as automatic. They compare models, line strengths, and broader spectral properties to judge whether stellar activity alone is sufficient. This uncertainty is important because the existence of a central active source at such an early cosmic age would itself be remarkable. To have an accreting black hole already contributing significantly only about 330 million years after the Big Bang implies that black hole growth begins very early and proceeds efficiently. That is not impossible within modern astrophysics, but it raises demanding questions about seeding and growth. A black hole of even modest mass must form from earlier processes and then gather matter rapidly enough to become active by the time the galaxy is observed. In a universe still so young, this requires swift assembly and a sustained gas supply. Gas supply is essential here, just as it is for star formation. A central black hole can only shine if matter is fed toward it. That feeding is not guaranteed. Gas carries angular momentum, meaning it naturally tends to orbit rather than fall straight inward. To reach the center, some of that angular momentum must be redistributed so that matter can spiral down into deeper gravitational regions in a compact, unsettled young galaxy. This may happen through internal turbulence, clump interactions, or rapid mass inflow. This same youth that keeps the galaxy dynamic may also create conditions favourable to delivering gas inward. Yet whether that inward delivery is strong enough to power a meaningful active nucleus remains unsettled. If active, such a central source would affect nearby gas differently from stars in some respects. Stellar radiation comes from many distributed points within the galaxy. A central active nucleus concentrates energy much more strongly near one location. Its radiation field can be harder, meaning richer in especially energetic photons, and its impact on surrounding gas can be more intense per unit volume near the center. It may also drive outflows, pushing gas away from the inner regions and altering the escape paths of radiation. In a compact galaxy, these effects could quickly reshape the innermost environment. A central source would not simply add light, it would reorganize the physical conditions through which other light must pass. Yet caution remains the proper tone in this region. Observations indicate that JADES-GS-Z 13-1 shows unusual properties consistent with strong ionizing conditions, while it remains uncertain whether those conditions require an active black hole. Hot young stars are already expected in such a system and may account for much of the observed behavior. An active nucleus is therefore not the default explanation. It is a candidate explanation that becomes relevant because the galaxy appears unusually effective at producing or releasing energetic radiation. This makes the central black hole hypothesis a measured inner layer of interpretation, rather than a settled component of the script structure. It belongs here because it is physically plausible, because it could help account for the local clearing around the galaxy, and because some scientific analyses consider it seriously. It does not belong here as a certainty. The observations do not compel one final reading beyond dispute. They open the possibility that the galaxy contains not only a compact stellar engine, but also a more concentrated gravitational engine at its core. If such a black hole is present, it would join the stars as another source of ionization and environmental change. If it is absent, the stars and leaking radiation already described remain the principal explanation. In both cases, the galaxy stays extraordinary. The difference lies in how that extraordinariness is distributed. With only stars, the power is spread through clustered young stellar populations. With an active nucleus, some of the power is concentrated into a very small central region wherein falling matter releases immense energy before disappearing from view. The physical consequences nearby could be substantial, even if the source itself occupies very little space. So this region is defined by restraint. It is the innermost candidate engine, a possible active central black hole, whose presence is suggested by interpretation rather than secured by final proof. It represents a way the galaxy might intensify its influence beyond what stars alone provide. It also represents a reminder that very early galaxies can contain complexity not immediately visible in their small distant appearance. In this uncertain core, gravity, gas supply, and radiation may meet in an especially concentrated form. Observations indicate the possibility. It remains uncertain whether that possibility is real in this galaxy. For now, the central black hole remains a careful scientific option, quiet but consequential, held within the evidence without exceeding it. At this depth, the region is no longer a place in space around the galaxy, but the evidence carried in its light. This is the spectrum, the spread of the galaxy's light into wavelengths that reveal physical conditions otherwise hidden by distance. A spectrum is not merely a record of brightness, it is a map of how much light arrives at different wavelengths, and from that pattern, astronomers infer distance, temperature, composition, motion, and the state of surrounding gas. For JADES-GS-Z 13-1, the spectrum is where the mystery becomes measurable. The galaxy is not unusual only because it is remote. It is unusual because the structure of its light contains information that seems difficult to reconcile with the expected conditions of such an early universe. One of the first things the spectrum provides is redshift. Redshift is the stretching of light to longer wavelengths caused by the expansion of the universe. The greater the stretching, the farther back in time the source is being seen. In very distant galaxies, light that begins in the ultraviolet reaches modern instruments in the infrared. By identifying where known spectral features appear after this stretching, astronomers determine how far the source lies and therefore how early in cosmic history it belongs. For JADES-GS-Z 13-1, this measurement places the galaxy at a redshift of about 13. That is not simply an impression of extreme distance, it is a spectral result. It means the source is being seen from an age when the universe is only about 330 million years old. This redshift matters because it fixes the context with unusual firmness. If the galaxy were closer in time, its surprising features would still be interesting, but they would not create the same tension with the expected state of the early intergalactic medium. The spectral measurement places the source clearly inside the Reionization era and near its early part. It secures the galaxy within a cosmic setting where neutral hydrogen should still be common over large volumes. The redshift therefore does more than locate the galaxy. It sets the standard against which the rest of the signal is judged. Within that redshifted light, the most striking feature is the strong detection of Lyman alpha emission. This line is produced by hydrogen under specific atomic conditions, and is one of the most familiar and useful signatures in the study of galaxies. Yet it is also one of the most vulnerable to interference from neutral hydrogen. In a universe still filled with broad neutral regions, a strong Lyman alpha signal from such an early source is not the easiest outcome to expect. That is why its appearance carries so much weight. The line is not merely present, it is strong enough to demand explanation. Its strength does not automatically mean the galaxy is intrinsically more powerful in every respect than all others. A line can appear strong because the source produces it efficiently, because the surrounding environment allows it to escape, or because both conditions happen together. The spectral evidence alone does not collapse these possibilities into one simple answer. Instead, it invites interpretation. A strong Lyman alpha line from a source at this redshift suggests that the galaxy sits in conditions more transparent than average, or generates a radiation field more intense than average, or benefits from an especially favourable arrangement of gas and motion. The spectrum tells that something important has happened. It does not by itself tell the whole story of how. Another major clue is the galaxy's blue ultraviolet continuum. The continuum is the broader underlying light across a range of wavelengths, distinct from sharp spectral lines. When this continuum appears blue in the ultraviolet, it generally points toward a young stellar population rich in hot stars, because hotter stars emit more strongly at shorter wavelengths. In a very early galaxy, such a blue continuum fits naturally with recent vigorous star formation. It suggests that the system is dominated not by old settled stars, but by youthful luminous ones. This matters because young hot stars are precisely the ordinary stellar sources expected to produce strong ionizing radiation. The combination of a blue ultraviolet continuum and a strong Lyman alpha line is especially informative. The blue light suggests a young stellar engine. The strong hydrogen line suggests that the environment around that engine is unusually permissive for the escape of a fragile signal. Together, these spectral properties support the picture of a compact early galaxy, with intense recent star formation and a surrounding region already altered enough to allow important radiation to travel outward. The data do not merely identify a distant object, they connect the visible light to a physical narrative of youth, intensity, and local clearing. Spectral interpretation also depends on what is absent or uncertain. Not every conceivable feature is measured with equal clarity at such great distance. Some lines may be too faint, shifted into difficult observational ranges, or blended with noise. This means astronomers build their interpretation from the strongest secure features first. In this case, the confirmed redshift, the notable Lyman alpha emission, and the blue continuum carry much of the burden. Observations indicate these traits clearly enough to support a coherent physical picture, while it remains uncertain whether additional weaker features would strengthen one explanation over another if they were measured more completely. This careful reading matters because the spectrum is the only direct messenger from the object itself. No close image can reveal its fine structure. No nearby probe can sample its gas. Everything known about the galaxy in a detailed physical sense comes from the light that survives the journey. The spectrum is therefore not a supplementary tool. It is the main instrument of understanding. Through it, astronomers infer youth, distance, energetic output, and environmental state. Without the spectrum, the source would be only a faint point of ancient light. With the spectrum, it becomes a physical system whose properties can be discussed with reasonable confidence. The data also help maintain proper scientific restraint. A strong Lyman alpha line may suggest a large local ionized bubble, efficient escape of ionizing radiation, or even an additional hard radiation source such as an active nucleus. But the spectrum does not by itself force a single exclusive explanation. It weighs possibilities. It makes some interpretations more natural than others. It narrows the field. The blue continuum favours a youthful stellar population. The early redshift confirms the demanding cosmic era. The hydrogen line shows that a signal usually vulnerable to suppression has survived. Together, these observations create a compelling but still interpretive picture. In this region, evidence is no longer inferred from surrounding scale or hidden structure. It is encoded directly in the measured light. Every conclusion about the galaxy's age, its likely stars, and the unusual openness of its environment passes through the spectrum. The light has crossed an immense distance, but it arrives carrying a precise pattern. That pattern is enough to show that the galaxy is truly early, that its stellar population is probably young and hot, and that its hydrogen emission survives more clearly than the wider age of the universe would seem to favour. So this section rests entirely within the data itself, in the measured wavelengths that turn a remote source into a scientific problem. The redshift anchors the galaxy in time. The blue ultraviolet continuum points toward a youthful stellar population. The strong Lyman alpha line announces a surprising degree of successful escape through an era still expected to be resistant. These pieces do not exist as separate curiosities. They belong to one reading of the same light. In that reading, JADES-GS-Z13-1 becomes not only a distant galaxy, but a precisely observed signal whose spectrum reveals why it should have been harder to see than it is. At the deepest scale of this subject lies the smallest ordinary structure involved in the whole chain of events, the hydrogen atom. Everything described in the wider regions returns to this level. The large young universe is filled with hydrogen. Reionization is the changing state of hydrogen. The local bubble around the galaxy is a region where hydrogen has been stripped of electrons. The strong spectral feature that makes JADES-GS-Z13-1 so remarkable is a signal produced by hydrogen itself. At this inner limit, the mystery is no longer framed by cosmic geography, galactic structure, or stellar populations alone. It is framed by the behavior of one electron bound to one proton, and by what happens when that simple arrangement is altered by light. A hydrogen atom is the lightest and most common atom in the universe. In its most familiar neutral form, it contains one proton in the center and one electron bound to it. That simplicity gives hydrogen unusual importance in astronomy. Because it is so abundant, even small changes in its state can shape the behavior of vast regions of space. Because its internal structure is simple, its possible energy states are well understood, and the light associated with transitions between those states can be predicted precisely. This makes hydrogen not only the main substance of much of the universe, but also one of the clearest traces of physical conditions across cosmic time. The signal at the heart of this story, Lyman alpha, comes from a transition inside the hydrogen atom. An electron can occupy different allowed energy levels. When it moves from a higher level down to a lower one, the atom releases a photon with a specific energy. Lyman alpha is produced when the electron falls from the second level to the first. Because the energy difference between those levels is fixed, the emitted photon has a definite wavelength. This gives the line its identity. It is not general hydrogen glow. It is a particular atomic event repeated across vast numbers of atoms. That event is easy to describe in isolation, but difficult to preserve in a young universe. A Lyman alpha photon is extremely sensitive to neutral hydrogen, because other hydrogen atoms can readily absorb or scatter it if they encounter it at the corresponding wavelength. This is why the signal becomes such a delicate probe of the early cosmos. The same atom that produces the line also tends to disrupt it when found in large neutral numbers along the path. Hydrogen is both source and obstacle. It creates the signal in one place and threatens it in the next. Inside a galaxy, Lyman alpha photons can be produced in several related ways. One important path begins with ionization. A hot star emits ultraviolet radiation, energetic enough to strip an electron from a hydrogen atom. Later, a free electron can recombine with a proton, meaning it joins again and forms a neutral hydrogen atom. In that process, the electron may settle through a sequence of allowed levels, and one of those steps can generate a Lyman alpha photon. Another path occurs when an already neutral atom is excited, meaning its electron is pushed up to a higher level without leaving the atom completely. When the electron falls back down, the atom again emits light at specific wavelengths, including Lyman alpha under the right conditions. In either case, the signal arises from the same atomic structure. This means the line is closely tied to active energetic environments. Hot young stars flood nearby gas with radiation. Hydrogen atoms are ionized, recombined, and excited in large numbers. The line becomes strong where hydrogen is being intensely processed by stellar energy. That is why a young compact galaxy with many massive hot stars can generate a prominent Lyman alpha signal. The same conditions that make the galaxy luminous in the ultraviolet also create many opportunities for hydrogen atoms to emit this particular line. Yet production is only half of the story. Once emitted, the Lyman alpha photon faces a difficult escape. Neutral hydrogen atoms along its path can absorb and re-emit it or scatter it in different directions, because the interaction is resonant, meaning especially efficient at this exact atomic transition. Even a modest amount of neutral hydrogen can strongly affect the photon's travel. The result is that a line generated efficiently inside a galaxy may still be hidden from distant observation if too many neutral atoms lie nearby. The atomic process is therefore inseparable from the atomic environment. A line exists not only because atoms emit it, but because other atoms fail to erase it completely. Ionization changes this balance. When hydrogen loses its electron, it can no longer interact with Lyman alpha in the same resonant way because the neutral atomic structure required for that transition is gone. This is why ionized regions are more transparent to the line. They remove the most efficient source of scattering. In the broader story of JADES-GS-Z 13-1, this is the atomic reason local clearing matters so much. A bubble of ionized hydrogen is not simply a region of changed gas. It is a region where the ordinary atomic obstacle to Lyman alpha transmission has been largely lifted. The large-scale transparency of the environment reduces, at bottom, to the altered state of countless individual hydrogen atoms. The same logic applies to reionization across the universe. On cosmic scales, the era is described as the transformation of intergalactic hydrogen from mostly neutral to mostly ionized. On atomic scales, that means immense numbers of electrons being removed from hydrogen atoms across vast reaches of space. The grand transition of the universe is therefore built from the repetition of one elementary process. An atom keeps its electron or loses it. If it keeps it, it can block certain signals strongly. If it loses it, the medium becomes more transparent. The fate of the observable universe at this stage depends on the answer repeated trillions upon trillions of times. In JADES-GS-Z 13-1, the observed line suggests that enough hydrogen near the galaxy has already been altered to allow the signal to emerge. Observations indicate the line is stronger than one might expect from such an early age, while it remains uncertain exactly how much of that success comes from local bubble size, gas motion, escape channels, or an additional hard radiation source. But all of those explanations work by changing the state or arrangement of hydrogen atoms. Each one affects whether neutral hydrogen remains abundant where it matters most. The final mystery, despite its cosmic scale, is atomic in character. This atomic scale also brings a quiet elegance to the problem. The galaxy is immensely distant. The universe around it is young, uneven, and only partly transparent. Dark matter halos, star-forming reservoirs, massive stars, leaking ionizing light, and perhaps even a central black hole all contribute to the larger picture. Yet the decisive signal depends on an electron changing level inside hydrogen, and on the presence or absence of nearby neutral atoms able to interfere. A vast era of cosmic history is read through one of the smallest ordinary structures in nature. So this innermost region is the hydrogen atom itself, the simplest abundant building block of the visible universe, and the direct source of the line that makes the galaxy so notable. Its electron transitions create the signal. Its neutral form suppresses that signal. Its ionized form permits greater escape. At the deepest layer of explanation, the galaxy that should not have cleared the early universe is not defined only by how large its bubble becomes or how bright its stars are. It is defined by what happens again and again within hydrogen, where a single electron, a single proton, and a single photon together determine whether a young universe appears closed or newly open. The galaxy remains small in the frame of the sky and remote beyond ordinary intuition, yet its significance rests in a sequence of simple, linked conditions. A young universe still holds much of its hydrogen in neutral form. Neutral hydrogen resists delicate light. A compact galaxy forms within a dark matter halo, gathers gas, turns part of that gas into hot young stars, and fills its inner regions with energetic radiation. Some of that radiation escapes. Nearby hydrogen becomes ionized. A local clearing grows around the source. Within that altered pocket, a fragile signal gains enough room to begin its journey. By the time it meets the wider neutral universe, it has a better chance to survive. Nothing in this chain requires fantasy. Each step follows known physics acting in an unusually early setting. What gives the galaxy its quiet power is not that it breaks the universe. but that it reveals how unevenly the universe changes. Reionization is not a curtain lifting at once. It is a patient opening, place by place, source by source, atom by atom. This galaxy appears at one of those openings. Its light suggests that even in an age still governed by cosmic fog, some local regions are already becoming clear. Observations indicate a source whose signal travels more successfully than expected for its time. It remains uncertain exactly how much of that success comes from clustered hot stars, favorable gas structure, unusually effective escape of ionizing radiation, or a possible additional central engine. Yet the uncertainty itself is gentle rather than disruptive. It does not erase the picture. It keeps the picture alive. In that calm uncertainty, the galaxy takes its place in the history of the early universe. It is not a contradiction. It is a sign that the first clearings begin sooner, more unevenly, and more locally than a simple story would suggest. Far away, in one small ancient system, the early universe begins to open.